Hello, everyone. My name is Ivan, and I'm here to talk about a project that I made. The title is a bit funny, but the project is as well funny, I think. I think everyone knows the Google dinosaur. Whoever played that game, please raise your hand. OK. Who doesn't know about the Google dinosaur? OK, so I'll make a few people happy today. Well, to begin with, Pterodactyls and Cactus is just a way to attract you guys. Yeah. Well, that's the dinosaur I'm speaking of. And my project, it's basically a way to learn artificial intelligence. I think that the most difficult thing to us to learn is by ourselves on the internet. And sometimes the content that you find on internet is too formal or maybe in a way that you cannot understand easily. And what I thought about when I began working with AI was, let's try to break this barrier and make it easier for other people that want to learn as well. This game is pretty simple. I mean, a child can play it in 5 minutes. And it consists basically in jumping cactus. And if you're good enough, you can see the pterodactyls. And if you're good enough, you can see the end of the word. Well, so how did all this begin? Was with a friend of mine called João and Tony, which is a guy that I'd never met personally, but we were on the team that was converting TensorFlow to Node.JS. In that time, last year, we thought about this project, and he said, oh, let's try to make a demo with something, and the idea came up for the game. So thanks them. And so how does it work to make a dinosaur learn to play a game that I will not say how to do it? So imagine that you have a program, and you cannot tell him how to do it. You can give it like ways to do things, but you cannot say jump before a cactus. Okay, so basically, what it does is that we abstracted the game in a way that robotics works. Everyone knows about sensors, and sensors are just a way to sense things, to measure things. And so we thought, let's add sensors to that dinosaur. And the first sensor that you think of about playing the game is the distance sensor. I mean, everyone wants to know the distance from the dinosaur to the cactus, because that's the most important thing to play the game. And after that, there is also the size sensor, which is like the length of this cactus. And what the size does is basically measures the length of the cactus. And also the speed is important, because the game, when it's getting more complicated, it's gaining speed. And as speed increases, you have to jump before or maybe later. And well, this has been abstracted. And so we have 3 sensors input. And basically, this is being constantly calculated from the image of the screen. Node.js reads that screen pixel by pixel and sees where those informations are. Okay. This is what basically does. It goes like scanning the screen to find the game position. And this is the really start of the program, where it finds where in the window, where in the screen the Chrome window is. So we do like a greater scan and then a smaller scan to get accuracy. This is the code. This presentation is on the squad, so if you want to download it later, I will not go deeper into code, but I will explain the big picture. After getting the information about where the game is on the screen, we start doing relative measurements from that point. So we basically look at the cactus from that position in game. This is what the script does. And after we do some measurements, we can think that the dinosaur needs to actuate. So like we need a motor, or we need something that will actually do things. And in that way, we thought about actuators. But it's not a true actuator. It's a virtual key press in the operating system, but it acts like actuator, okay? So basically, it can jump, and it can duck. Oh, yeah, it can duck. Yeah. I think everyone will disconnect to the Wi-Fi now to test it out. So now it begins the part where the funny can be more funny. We have inputs, and we have outputs. A programmer would look at this and say, there is a gap in between them. Let's put some code on it. Okay? Let's add something there to fix this problem, to solve this problem. And the thing is, the problem can be solved in many ways. You can put a if distance is greater than then duck, or maybe do something else. But the truth is, I was trying to learn about neural networks and also genetic algorithms. And I started to learn about how neural networks works. Whoa. And I saw that usually we put code in the middle of it, but the truth is that whatever code we put on, we can map that to a function. Maybe a continuous or not continuous, but we can map that to a function. Like, I give you x and you give me back y. I give you the distance and you give me back the amount of press that I need to do on the upper key, okay? Or maybe I give you distance, speed, and size, and you give me how much I should press the up key. And that's basically a game that we can think and connect neurons, okay? Neurons are just the small piece of puzzle that you can do to connect the inputs to outputs. If you think about this, you see that it's a really simple problem, and we can understand it better if you think about proportionals, okay? If you see the distance and the up key, and you wonder, what should I do when the distance increases or decreases in this case? If the cactus is coming far, actually near you, you want more to press the up button than to release it, okay? And if you think about the size, the greater the size of the cactus, you want to jump a little later in order to get to the end of it. If you jump in the same distance prior to the cactus, you will end up in the middle of it. So we can see that the distance may be proportional or inversely proportional, and everything is proportional or something like that. And if you take a look at those neurons, there are actually functions that you give inputs and they output something. In order to understand a bit more, a neuron is just a bunch of inputs that you can aggregate into an output. And each input has its weight, and you multiply the value that is currently there by its weight, and you sum all the inputs, and you add what's called a bias. I took a little longer to understand the bias, but it's basically a sum in the end of it. And if you think about this really simple neuron, if you input 0 and 0, it will output 0. If you input 1 and 0, 1, 0, 1, 1, and 1 and 1, 2. And you see, OK, that's pretty basic math, right? But it's doing a OR function. If you think that the output greater than 0.5 is true, then that's an OR function, right? And if you want to change it to an AND function, it's basically making it harder to get to 1. So basically decreasing the weights in the inputs. And that's basically what's done here, and the AND function. And if you think that, OK, you can do OR, you can do AND, how can we do like more complex math with it? You can aggregate many neurons, and you get like a more customizable function that can map inputs to outputs in a better way. Or maybe with more precision, But if you give it too much like space to grow, then you may be overfeeding your neurons, and your neural networks may not work or not be good. This is an example of XOR. You need 2 neurons to make it work. And it's basically like summing things if they are the same and subtracting if they are different. And the XOR is basically this function here. And if we go on and see about the big picture of a neural network, this is a pretty simple one, but it has 2 inputs and 1 output. And every single circle in that image, it's not code. It's just a number, nothing else. Just a single number, 0.7 minus 3, 357.58. I mean, it's just a number. It's nothing else. And everything that is on that graph, the connections, are what makes this neural network that way. So I could delete parts of it. I could delete arrows. But the main thing here is we have layers, and we have like a shape for our neural network. Well, to do that, I used Synaptic, which is a really cool library for Node.JS and JavaScript. It basically wraps all the neural network parts for you, and you have the inputs, the outputs, and you can create many layers and many shapes for your neural network. And also, to simulate the keys in this project, we used Robot.js, which is a library for you to simulate keys, to read color of pixels in the screen, and also to click on the mouse and move the mouse around. A tip that I give to you is that don't move the mouse in the code and put a loop inside it, because when I did it, my mouse was clicking in a position and my terminal was in another, and I had to reset by force. Yeah, there was no way to Control-C because it was clicking there and it was not fast enough. Yeah, damn. So let's abstract this in order to get a closer look about how the genetic algorithm works. So basically, this does nothing. I mean, it's not intelligent. It will never be intelligent. It will never see cats as funny. But we can train it to do something good. And that part, the training part, is the one that takes much, much, much more time than usual, because you have to train. I mean, have you ever tried to score a football point? I'm really bad at it, and after 22 years that I'm living, I'm still not good enough, you know. And that's training, you know. If I train a lot, I will be better in the future, but I don't. So let's think about this neural network and forget about all the connections. Just think about the values, okay? What really matters in that neural networks is the values. Now, we forget about the shape, and we do a simple transformation to put it like in an array. So that crazy thing, it's just a simple sequence of values, okay? And if we see each circle as a number, as I said, you can copy and paste those numbers in another neural network with the same shape, and you have the same behavior, because it's actually the same program, okay? So see this form, those values that are inside, that can be inside as a program, okay? And now, let's take this and duplicate, okay? Start all the values with random numbers. I'm not sure what's right, what's wrong, but I will start randomly. And so you create what's called a generation of genomes, or maybe DNAs, or maybe whatever you want to call, but it's a generation of like individuals. They are not alive, so that's okay. And basically, this is the code that does it. It's just like, why it's not full, add one more to the list. And after that, here is the part where we do something really special with them, which is test them. I mean, how can you know, how can you select the best ones from a generation? You have to test them. You have to put them in practice. I'm not good at games, but let's suppose I was at CS, Counter-Strike. How do you see if a user is better than the other? You put them to play and see whoever does more killing, or maybe you are in a football game and you see which team does more goals, or maybe you are in a contest about who eats more hot dogs, and hot dogs is your fitness. It's your how much good you are at something. And in this case, we go and test each one of them, and we see how good they are. And we sort them by that number. And after that, we have like a ranking. And that ranks help us to kill the worst ones. I would probably be in the worst ones there. Yeah. So basically, we select the best ones. And after we have the best one selected, this is the code. You can check it out on the presentation there. We have to propagate what's good in their genome or in their DNA. And that's pretty hard, because if you know what part is best, then you already know how to be better, how to be the best one. I mean, if you know that the third circle should be 3.0, then you already know what's the best thing to do, right? So we cannot do that. We need to do random things here. And that's the funny part. To begin with, we choose like individuals, 2 by 2, and we do a crossover them, which is basically get a random part from one individual and a random part from another one, and you just cross over. And you do like this. And after that, you have like a new individual. It can be good. It can be worse. I mean, it can be better. It can be worse. And it can be equal the father and the son. The father or the mother. Yeah. OK. There is no father and son and mother here. But the important here, important thing here is that you have a new genome that you haven't tested yet. And let's imagine for a moment that all the generation that started it was filled with zeros, okay? Just for example. All the crossover would result in 0 genomes, right? If you select randomly one number from and the other one and you merge them, it will be 0 because either of them are all zeros, right? So that way, you wouldn't be, it wouldn't be possible to improve. And the thing that makes the magic happens here is the mutation, which is basically adding or multiplying, or adding and multiplying a random number in a random way, in a random sequence. Yeah, many random things. And you actually end up having a new genome, okay, that can be better and can be worse. And after that, here's the code. We just do that process again and again to fill out the genomes and fill out our generation. And after this process is done, you may think that it's complete. But actually, it's just one part of an infinite possibility. Because if you do that again and again and again and again and again, you repeat it many times, it will converge to something that you call good. Okay? So that's basically what a generic algorithm does, and basically what this project does. I will go for a demo now. This is how it basically works. Let me show you. First thing is to not have internet. Yeah. Is it on the screen? Let me reduce a bit the size. So I will open Google Chrome. Oops. Okay then, so let's do that again. I will play the game first time just to show you that it can duck. Yeah. And then I will hit enter. As you can see, the mouse moved. Look at the mouse, it's here, okay? I will end the program, it's here. I'll press enter, whoops, okay? And it already detected where the game is on the screen. So basically, it knows where the game is. And if I play it, this is me playing, okay? It will basically show those values in real time. So you can see the distance decreases, the size is showing when there is something, and this is me dying. Also, you can see that the game status, you can see stopped. The game status here is over. It's reading this game over text and saying, okay, the game is over. So it knows when to end. It's playing, as you can see here. It's a bit small, but that's okay. And also, you can see the fitness here, which is the important part. Every time I jump a cactus, it counts 1, 2, 3, 4. And that's how it knows how many points a generation has scored. I will reset it and go to the code just to set a flag off. I'll show this later. Okay, and what I did after programming, I said, okay, let's test it, right? Let's hit a button and test the program. And I hit the button and yeah. So it kept it on this for hours. I mean, literally hours. And the cool part is that I didn't know if my program would work. I didn't know if it would never work. I didn't know if one day my son or maybe me would see it working. But I knew that it could work, right? And just to explain what's happening here, you can see that it's testing out each genome. And every time it ends, it tries the next one. And when it ends the generation, which is 12 genomes, it deletes the worst ones, do the crossover, do the mutation, and try again every generation, okay? So after attempting many times and watching it literally in my bed, sleeping, I woke up and there he was, jumping cactus, but not Pterodactyls. And I said, oh, great. Let's do some modifications and try it again. And then I forgot, OK, where is the save button? And OK, implemented the save button. It's here. You can press it, and it saves the genome. But I didn't have. So I started implementing more things on top of it. And the cool thing is that after some time, you see that this cycle repeats so many times that you say, OK, let's at least do something that will speed up things here. So in order to do that, I made this flag here, which is so cute. But it basically, if you see here, it checks the experience of a genome. So it's basically before running it, before testing it out in the game, it sees if it can actually jump or duck, or do at least 2 actions. And if it doesn't, what it means is that it cannot do anything, so it will die, certainly. So when we enable that flag, it can be much faster to see the results. Yeah, this is not good. But I mean, he can jump. And we are already on generation 8, which is pretty lucky. Yeah, I will run it a few more times in order to see what can happen also. Generation 11, oops. Let me run it one more time. Okay, let it die. Oh. Yeah, this is what I saw a lot. I mean, it doesn't check if it's good. It only checks if it can do at least something. And, well, basically, that was the story. And my results were pretty cool because I didn't expect it. So I will show you what it happens when we run with a generation that I call Ninja. As you can see, its normal state is to duck. And that's a pretty different species from dinosaurs, I guess. But the important thing here is that I didn't notice that when it ducks, it falls faster. So it ends up being better to duck always as being stand always. And the second thing is that it didn't see the Pterodactyls, and it just passed by them really usual, okay? And the third thing is that as the environment changes, Chrome did change the game, and it made it be dark after 700 points, and that's the end of the generation because it can see the dark. So in any way, thank you very much. Oh, it's pressing a lot of keys here. I have to finish it. Okay, so a gift to complete, and when I posted it on Reddit, people said, not really related, but if robot dinosaurs take over the world, I won't even be mad. Yeah, thank you very much, people.